Xavier. I hope you're fine. All right, you're welcome to chemistry. Hope you had a small break. I know it wasn't that big. You were busy doing the activity that I left. But let's do chemistry, and you can continue the activity after we're done with chemistry. I'll not give you a chemistry activity so that you first concentrate on the one for biology and finish it.
Okay.
Again, if you don't hear me well, please you type in the chat box or you tell me so that I can probably change something to increase my internet broadband. Okay. So today in chemistry, we shall concentrate on atoms, molecules, and ions. This is one of the first topics you are supposed to cover in Senior 5. It falls partly in physical chemistry and also a little bit of inorganic chemistry. So this one falls between both. In the curriculum, we normally put it in physical chemistry, just it's the beginning of physical chemistry. And then when you go to inorganic, you start directly on the periodic table, the trends. So today we shall do atoms and molecules and ions. Okay, very good. Let us start with the atomic theory of matter. There's so many people that are credited for this theory. We have people like Leucippus, Democritus, Lucretius, Aristotle, who thought that they were nuts. John Dalton, who is huge in this, and you can see his picture there, is the one we shall concentrate on because he nailed most of the facts about atoms that we know today. He revived the idea and made it science by measuring the atomic weights of 21 elements. That's the key thing because then you can see how elements combine. So Dalton's work is huge for us as far as chemistry is concerned. This is how he postulated, Dalton's postulates, that each element is composed of extremely small particles called atoms. In actual sense, he said tiny balls make up the world. Okay, this one can also be seen in the Bible. Those who are Christians, when you open in Hebrews, I think it's probably chapter 5, verse 11, if I'm not forgotten, says, I know the quote, it says, by faith we believe that the world was made from things that are unseen. The things that we can see are made from things that are unseen, meaning that we all know that we can't see atoms with our own eyes. So the atoms make up the world. You can easily interpret that verse in Hebrews like that. And I think Dalton probably read that somewhere there. This is why he said tiny balls make up the world. All atoms of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of other elements. Here, Dalton meant that the atoms of oxygen are way different from the atoms of nitrogen. That's what he meant. He also said atoms of one element are not changed into atoms of a different element by chemical reactions. Okay, you can't change atoms of oxygen to atoms of nitrogen. It is impossible. Atoms are neither created nor destroyed in chemical reactions. As far as Dalton knew, they couldn't be changed at all. Now, being changed now has changed due to the science we have these days, and we shall see why. But he nailed it when he said that atoms of one element cannot be changed to atoms of another element. That was absolutely correct as far as we know today. So here, this is what he meant, that if oxygen was reacting with nitrogen, okay, oxygen was reacting with nitrogen, we would have the same atoms that were reacting this side, we will have them this side represented. Okay. Yeah, that's what he meant there. Please remember to ask questions whenever you have them. Okay. And he also said that that the chemistry here happens when these atoms rearrange. So it's all about the rearrangement. Like, for example, here we have ammonia being formed. You see that you had three hydrogen atoms and one nitrogen atom. They rearranged to form the ammonia. Okay, he was right on that. These reactions are all about rearrangement of atoms. Okay, and that introduces us to the law of constant composition or conservation of mass. So the elemental composition of a pure substance never varies or never changes. The relative amounts of each element in a compound does not vary. Ammonia will always have three hydrogen atoms and one nitrogen atom. That will never change. You'll never find ammonia changing. And the law of conservation of mass says that the total mass of a substance present at the end of a chemical process is the same as the mass of substances present before the process took place. What does that mean? Now, that means that if you have a certain number of atoms amongst the reactants, once the reaction is done, you should have the same amount of atoms on the product side. This is where the idea of balancing equation comes from. Balancing equations. You see here you have 6 hydrogen atoms, 2 nitrogen atoms. The total of this is 8 atoms. It should be the same this side, okay? You have 2 nitrogen atoms and 6 hydrogen atoms, which makes 8. Meaning the masses are conserved. If you have any questions, please ask. So that's the law of conservation of mass. Let's look at an electron. This was Thomson's model. He measured the charge of an electron. If you take physics, you look at this more in physics. But here is some of the things that he did. We have, when he was measuring the charge of an electron, which he found out to be 1.76 to power 8 coulombs per gram. He did it by manipulating the magnetic and electrical fields, and observing the change in the beam position on the fluorescent screen. So you have your charge here, which is going to release electrons from this metal element here. So electrons are going to move through this tube, right? And once here where you have electrically charged plates and a magnetic field, what he did, he just played around with these two fields, the electrical field, okay, and then our magnetic field. So for example, he could bring in a negative charge electroplate and see how the electrons would distribute on the fluorescent screen. And maybe on the other time, you'd bring in the magnetic field and then see the distribution or the electron parts on the fluorescent screen. This is how he came up with the value using the voltage here. Okay. And he measured the the charge of an electron to be this. All right, so now we know the charge of an electron. That one will help us in calculations later in physical chemistry. Let us look at radioactivity. This is the spontaneous emission of radiation from an atom. It was first observed by Henry, and his last name is this word, Becquerel or something like that. I have no idea how to pronounce this name. But it's Henry. But also, another couple that is credited with the study of radioactivity is Marie and Pierre Curie. To me, I think mostly Marie Curie because she dedicated her life for the study of radiation. She did a very, very great job. I'll tell you a story about Marie Curie later on in a few slides to come. But in this age, women were not credited for anything. Even for her to be credited for this study, it is huge, huge. This is why most times you see the husband mentioned every time she's mentioned. The age was terrible for women by then. So we see radiation, that atoms can release radiation, emission of radiation from atoms. What comes out is, from the radiations are actually subatomic particles. We shall see what subatomic particles mean. Here is radioactivity by Ernest Rutherford. He observed the particles that come out of these atoms. And we have the alpha particles that are attracted to the negative electron and beta particles that are attracted to positive electrons. That's all you need to know here. Most of these are just explanation of how he did it. Here is Marie Curie. And this is actually tell you the story too on this one. Hey, Marie Curie, you are looking more radiant every day. Now, before you laugh at this, let me tell you the story. So Marie Curie was working in the laboratory, always with his husband sometimes probably, but she dedicated most of her life to study radioactivity. Now, as you know that radioactivity that going wrong in your system, your organs are affected and many things. Okay, my internet was bad. I hope it is now okay. Type in the chat box, I'll see it. But as I was saying, Marie Curie worked a lot on radioactivity, and then they started the radiation started affecting her seriously, started affecting her organs, and she started even changing. Okay, her skin tone changed, and eventually she died from the radiations that she was working on. So when you see this, that she's looking radiant every day, in her body that are making her look like that when someone says something like that. And yeah, she eventually died from these radiations because of working on them. Radiations are very, very dangerous. You can, I guess you've heard of the story of the atomic bomb being still affected even up to now due to the radiation. So radiations are not good for our bodies. And Marie Curie literally dedicated her life to studying radiation because the radiations eventually killed her. Okay, the nuclear atom, Rutherford postulated that it is the first small dense nucleus with the negative electrons around outside of the atom. But Other subatomic which were discovered in 19 that discovered by 32 after, and it's like that of a proton, but they don't have a charge. Someone has a question? Faith?
No, your network.
Oh, my network.
Yes.
Is it better now?
Yeah, a bit.
Okay. It's better, that's good. All right. So I was talking about the neutrons. They were discovered in 1932. And we know now that they don't have a charge. So those are the subatomic particles that we are not looked at yet. Here are their charges and their masses in atomic mass units. Okay. These ones you use them later on in the future, but not now. Here is another story. Here came two guys fighting for an atom. These two men claim ownership of this atom. How can we solve this conflict, Lord? The Lord was like, split the atom in half. But when you split the atom, it releases a lot of subatomic particles which contain a lot of energy, and this happens. It's like a nuclear reaction. And this is the same thing that happened in Japan in 1945. Okay, so when you split an atom, that's what happens. Therefore, it was a bad idea by the king to tell them to split the atom. They could probably have died. All right, let's look at now the symbols of elements. I know you have looked at most of these in O level, but it's always important for us to repeat them because you are going to use them in the next topics. So we have the symbol of an element, which is always represented like this. Now, for example, this is carbon, it's a capital C. Elements are always symbolized with 1 or 2 letters. Down here, we always have the atomic number, which represents the number of protons or the number of electrons. Not both. There's a word O here. So it's either number of protons or number of electrons. Okay. All atoms of the same element have the same number of protons. So we denote it with the letter Z. Every time you see Z, that is the atomic number. We have the mass number. The mass number is the number of protons plus the number of neutrons. So this is a combination of two. When you add protons and neutrons together, you get the mass number. The mass of an atom in atomic mass units is approximately the total number of protons and neutrons in the atom. So when you count the number of protons and neutrons in the atom, you always find that it's almost the mass number. It's always approximately the mass number. That's why you'll see, for example, that of carbon, the mass number, you'll find it like 12 point something, but it can't go beyond 12, okay? Unless it is a different isotope. And that introduces the idea of isotope. Remember to ask if you have questions. Isotopes and by the number of atoms of the same element. Okay, it's back. My internet was disturbing it, but I guess it's back. Atoms of the same element. The actual difference is neutrons. Okay, protons are the same, electrons changes in that number for each. Example, we have carbon 11, carbon 12, carbon 13, and carbon 14. In carbon 11, we have 5 neutrons. In carbon 12, 6 neutrons. In carbon 13, 7 neutrons. And in carbon 14, 8 neutrons. That's the difference. The difference comes in the number of neutrons. Okay, it is the one that causes the change in the mass numbers. Let us look at the atomic mass. How was it measured? So the atomic mass and the molecular masses can be measured with great accuracy using the mass spectrometer. Heavier ions turns less in the magnetic field. Okay. So this mass spectrometry, we shall look at a whole topic about it. But here is a brief explanation of what happens in a mass spectrometer. So you have a source or a sample of an element which you want to measure its atomic mass. Okay. In the mass spectrometer, we have the heated filament, okay, ionizing electron beam. Okay. We have the vacuum pump to make sure that in here there is a vacuum. We have an accelerating grid here. Of course, we have the beam of positive ions that are coming from the sample. We have the magnetic field here, our magnetic field. Okay, and if, for example, we have the separation of ions based on the mass differences, we have a detector here and a slit. Okay, now if you have a sample, here it's gonna get heated and ionized. Okay, going from have it ionized, and then its speed is accelerated here in the grid. As it passes through the magnetic field, ions are deflected. Okay, the heavier ones are deflected less, and the lighter ones are deflected more. Okay, and this is what happens. For example, here, the chloride ions with 37 mass number are deflected upwards here, and then the one with 35 is deflected here. Okay, so that is the mass spectrometer. That's how it works. It's just all about deflection of the atoms, the heavier ones from the lighter ones. And that's how we know even this, that's how we know the isotopes of different elements. If you have any questions about this, please ask. Like I said, this is another topic where you can even, where you have calculations involved. So utilize that. As when we get there, we shall look at it in details in the future. Remember to ask questions. Let's look at the average mass, how we find the average mass. You've heard of relative abundance. So this is where it is involved. So because in the real world, all the elements exist as mixtures of isotopes. Okay, there's no way you're going to find, oh, this is chlorine 35, this is chlorine 37. And you see it there. Now in nature, chlorine 37 and chlorine 35 are mixed together. Okay, remember they're atoms of the same element. So, and we measure many atoms at a time, which we call natural abundance. The average mass is calculated from the isotopes of an element weighed by their relative abundances. Relative abundances means who has the biggest percentage. Is it, for example, here, when you look at magnesium, here are its isotopes. These are the isotopes of magnesium. Magnesium 24, magnesium 25, magnesium 26. Remember, they exist in a mixture, but here we have separated them. Now, amongst all these, magnesium 24 has the highest percentage, which we call abundance. It has 78.99%. It is followed by magnesium 26, and then magnesium 25. Those are their abundances. The atomic masses of each in atomic mass units are here. Okay. Now, to find the actual mass of magnesium, we are going to to utilize these values, these abundances. So they will ask you what is the average molecular mass of magnesium. Okay, and this is it. So what we do is that we get the percentage, which is here. This is the percentage. When you divide 78.99% divided by 100, you get this. So this is the percentage times its relative abundance. I mean times its atomic mass, not relative abundance. Times its atomic mass, which is this. Okay. Then we add that of magnesium 25, which is the percentage is 10. When you divide it by 100, you get 0.1. It is here times its atomic mass plus, okay, the one for magnesium 26 times its mass also, which will give us these values. And when we add them together, the average mass of magnesium we get is 24.31. So this is how we find it. Let's use their isotopes and their abundances to get this. If you have questions, please ask. You can type the question in the chat, or you can just unmute your audio and ask. All right. Now, let's look at the chemical formula. The subscript of the right to the right of the symbol of an element tells the number of atoms of that element in one molecule of the compound. Okay. So, for example, here in the formulas that we have, if you see this, the 2 on hydrogen represents the number of atoms of hydrogen in water. Okay. And almost all none. Sorry, my network disturbed a little bit, but I'm back. Okay, here we are. We're still talking about this, the molecules. Now we have that of water, carbon dioxide, carbon monoxide, methane, hydrogen peroxide, and oxygen. And these molecules are mostly always of non-metals. If you've watched this movie, you'll enjoy this one. Molecules after chemical reaction. This is what happens. They are gone, reduced to atoms. So when molecules react, they become reduced to just atoms. That's what happens to molecules, like what happened to Thanos in this movie. So let's look at the atomic molecules. The atomic molecules are those molecules that have two atoms. They contain two atoms. And these are the ones on the periodic table. We have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the ones that we call the atomic molecules. We can also look at the types of formulas. We have the empirical formula, and these ones give the lowest whole number ratio of atoms of each element in a compound. For example, when you look at ethane, its empirical formula is CH3. And the molecular formula is C2H6. So when you double the empirical formula, this is what you get. Okay. Molecular formulas give the exact number of atoms of each element in a compound. So for the molecular formulas, it is the exact number that is represented. So in ethane, you only have 2 carbons and 6 hydrogens. The empirical formula gives a ratio that in ethane, the ratio of carbon to hydrogen is 1 to 3. Okay, it's just a ratio. The molecular formula will give you the exact number of atoms. Okay. The types of formulas, again, we have also the structure formulas. In the structure, I just draw the structure of each. These ones we shall look at in organic chemistry, so you don't need to worry about that. Let's look at ions. When atoms lose or gain electrons, they become ions. Often, they lose or gain electrons to have the same number of electrons in the nearest noble gas as the nearest noble gas. So we saw this probably in your own level when you're looking at bonding, right? When atoms lose or gain electrons, they just want to be stable. They get a stable outermost shell. Okay. Cations are positive and are formed when elements on the left side of the periodic table. Those are the cations. They are always here on the left side. Anions are negative and are formed by elements on the right side of the table. Here are our anions. These ones lose, and then these ones gain. Okay. Please, if you have questions, ask. Monoatomic ions, those are the ions that only have one atom. And here they are. On the periodic table, we have here. All right, and then these ones, metals and the non-metals. Usually, metals become cations and non-metals become anions. Okay, and we can look at ionic compounds now. Compounds that are formed from ions. These are the normal reactions that you've encountered before, so they're very easy. For example, when you look at how we form sodium chloride, sodium ions react with the chloride ions to form sodium chloride, meaning this is an ionic compound. This is formed from these ionized elements or atoms. Everybody gains or loses electrons to be like the nearest noble gas. Compounds are always electronically neutral. And that's how we form ionic compounds. We can also look at briefly writing formulas. This one I know you're good at it. For example, here we have magnesium nitride. So what you do, you just write the charge of magnesium or its valency at the top. And then you exchange those valences. The one for nitrogen will go to magnesium, and the one for magnesium will go to nitrogen to form this formula. That's how we form formulas. I hope you have remembered that. Remember, I'll send out these notes so that you see them. You'll go through the most common cations that we have, and here, these are the most common cations. Their formulas are right there, and then their names are also given here. These ones, you should be knowing them by now. You should know these by now from your O level and all that. You should also know the most common anions. Okay, here they are. You go through them to remind yourself. And then we have polyatomic anions. These ones you may not have concentrated on them most in O level, but now you need to know them. For example, we have the thiocyanate. You look at it so many times. You have the nitrite, the bisulfite, the bisulfate, the hydrogen phosphate, the hydrogen phosphate, the hypochlorite, the chlorite, and very many others. These ones you need to go through them and remember them. Okay. We have oxyanions. Okay. These ones contain oxygen. They contain only two. When there are only two oxyanions involving the same element, the one with fewer oxygens ends with "ite." So, for example, when you look at a nitrite, and a sulfite, they end with "ite" because we have another anion that has more oxygen atoms. And here we have a sulfate. Okay. For those ones, they end with "ate." And here we have the nitrate. Okay. Whenever you find that the oxyion has more oxygens than the previous one, you just know that one will end in "ate," like a sulfate and a nitrate. Those ones we call them oxyanions. So that's the difference. Less oxygens end with "ite." More oxygens end with "ate." See that? That's how we name oxyanions. You look at their patterns here to see the chlorate, the perchlorate, hypochlorate, chlorite, how they are different from one another. Again, we're using the number of oxygens. Okay. All right. Examples of naming inorganic compounds. You will look at these namings. I know you know them very well, like sodium chloride, ammonium nitrate, how we name them. While we end with "ide," okay, especially if we have an anion with a polyatomic ion. For example, if you have a sulfate or a nitrate or a chloride, then you're going to name it different from when you have just a hydrogen or just a chloride ion. So make sure you remember that and go through it. It's the same thing with naming other examples here. It all depends whether you have a polyatomic ion or just an ion. When you look at hydrogen, it's a little bit different. Hydrogen, when it's negatively charged, we use hydride. When it's a cation, it is in an acidic form. And here is our acidic nomenclature. You can go through it and understand how we name hydrochloric acid. For example, if the anion in the acid ends with "ide," change the ending to "ic" acid and add the prefix hydro because of hydrogen. So for example, HCl will be hydrochloric acid, HBr will be hydrobromic acid, and HI will be hydroiodic acid. If the anion in the acid ends with "ite," change the ending to "as." For example, in this one we have chloride, so the acid will be hypochlorous. That's the difference. That's the difference. Let's continue shortly and it will be it. So this is how we name acids. Please go through this and understand how we name acids. I also go through how we name compounds, tetra, where hexa comes from, and things like that. All these prefixes, you can go through them and understand where they come from. And that's it for today. Lastly, please think like a proton and stay positive. That's my last message for you today. Take a break. I know later on you have geography. You can go for that later. Thank you for attending. I hope you go through our work here using these links and see more examples of this unit. See videos that we have there. If you subscribe, you'll be able to see all that, good explanations with better pictures and all that. They'll be through these links for you to utilize. I am going to send these notes for you to go through them. I'm not going to give you an activity for chemistry because I want you to finish up the activity for biology that I gave you earlier on. Okay, well done. Nice lunch. Thank you very much.
Thank you, sir.
You're welcome. Please, you can go on and finish up the biology work. Thank you for attending today. Let me send this work in the group.
Baiknya dah. Why teacher?